Okay, good morning. Welcome to 40. I have good news for you. If you haven't seen that yet, the quiz is graded and you can download your score from BSpace. Also, the mean is over 80, and I think 30 or over 30 students got 100 points, so that's good. I guess sort of the delta between 80 some means 80 some and 100 is probably largely attributable that a little bit nervous, making a small mistake here or there. So if it's that, if you made a small mistake or something, nothing to worry about. I've told you already, in the midterm exam and of course also in the final exam, you will have more time available than in the quizzes. The questions also will be harder, so there will be more opportunity to actually do real thinking as opposed to just apply stuff that you learned and now replicate almost like a schema. But on the other hand, if you didn't do so well in the quiz, or if there was a question that really you didn't know quite how to answer, now is a very good time to come to the office hours, talk to one of the graduate student instructors, or myself, clear up any problem you may have about that. The class pace is going to speed up. We'll talk about more interesting but also a little bit more complicated material, and that will continue throughout, so never get behind. And yeah, look at the quiz as some form of feedback. Are there any questions? Okay, great. So look at it, and if you get any questions, then please again come and clear them up. We have about roughly 2 weeks, I think, 2 or 3 weeks, 2 weeks to the first midterm. So I will talk more about what is going to be on that midterm and what the questions are going to look like a little bit later as we get a little bit closer. I've also posted a sample midterm on the website, so you can already look at that one. There are some questions on it that cover material that we haven't talked about yet, but that we will get to this week. And then there are many more questions on that midterm exam than on the actual midterm. Okay, so don't get scared that I will bombard you with 10 full score long questions. Of course, that's just so that you have maximum possible ways to sort of familiarize yourselves and check that you really know the material. Okay, so with that, let's get back to what we talked about on Friday. We sort of ran out of time, but we looked at the technique that allows you to analyze every circuit. It's a sort of a schema, almost like a program. In fact, it's a scheme that can be programmed very easily into computers, and we'll look into that also in probably next lecture. But anyways, here is a circuit that any of these techniques that we've looked at so far, voltage dividers, parallel series resistors, and so on, even source transform, it just doesn't work here. If you have a circuit like this one, you're back down to KCL, KVL, and constituents equations of the elements. So then we have a sort of a recipe developed last time that allows us to write down a bunch of equations for a circuit like this one. And then we can solve these equations using techniques that you learn in one or the other math class, and we'll get the right answer. And it works always. Okay, so let's try to recapitulate how we go about something like this. What's the first thing we need to do? Okay, I can't quite hear you, but I assume you said we have to identify a common node or a ground node. Now, in this particular case, that's easy because one is already given, right? The symbol on the left side. Sometimes there is none given. Well, then you pick one node, the one you like best, and assign the ground to it. Later, you will find that there will be, based on your experience, there will be some nodes that are better candidates for ground node than others. But in principle, it's arbitrary. It works always for any ground node. Okay, so what's the next thing we need to do? Anybody else? Maybe back there. Time to wake up. Yes. We have to find? Okay, so, oh, that's great. So you read the book, that's wonderful, and there you read about essential nodes and non-essential nodes and God knows what. I keep forgetting that stuff. Actually, you know, the book, in circuit design, of course, there is one right answer, but there are lots of ways on how to get there. And sometimes the book has one way and I have a slightly different one. And so I'll show you my way. In my way, you just have to identify which nodes or which node voltages are unknown. Okay? So we will go through all the nodes. Here is a node. Is the voltage at the node voltage at this node unknown? No, it's 0, right? What about this one? This one's unknown, right? So we give it some name, let's say VA. Okay? Then we pick another node. Is it known? Is it unknown? It's known. What is it? V1, right? So this one, VB, VC, VD. Okay? So I think we haven't forgotten one, right? All right, so we've identified all the nodes where the node voltage is not known. And now we apply this miraculous technique, and then all these node voltages will be known afterwards. So we will have to write equations, one for each of these nodes. Let me choose a little bit a darker pen. So I always label my equations so that I find them and make sure that I haven't forgotten one by accident. So for example, VA. Well, in node voltage analysis, we simply apply Kirchhoff's current law to every one of these nodes that we have there. Of course, we know how to do that. We'll do it very formally here. Call this IA, IB, IC, and ID. Okay? And then, of course, the sum of all these currents, note that I chose the same direction. All of these arrows leave the node. Okay? Therefore, the sum of all these currents have to be 0. So now we write directly an equation for all of these currents. So what about current IA? How are we going to go about that? Okay. So we figure out what is the voltage across the resistor in the direction of the current arrow. Why? Because then Ohm's law has actually a plus sign like we are used to and like we think it ought to have. Okay, so it's VA minus V1. That is the voltage across resistor R2. And if we divide by R2, that's the current IA. Okay, then we are going to do the same thing for IB. Well, that would now be VA minus VB over R4. I'm writing it just myself. I assume that you can follow. Otherwise, I invite you, like always, stop me, and I'll be happy to explain it to you, and we can discuss it in detail. Okay, then IC, well, that is VA minus, you know that the other side is VC over R7. And then finally, what is ID? That's just equal to I2. And then that whole thing is equal to 0. Okay? So we have 4 unknown nodes, so therefore we will have 4 equations. It's a little bit tedious to write them all. Well, let me write VB also. VB, so there we would have, well, we can now, maybe I should choose a different color, so otherwise, so IX, IY, and IZ. Okay? So IX, what is that? Well, it's the voltage VB minus 0 exactly, divided by R3. So it's always convenient when we have voltage sources or when we have a ground node, so then we know the voltage already on that node, and that simplifies our equation a little bit. Okay? So then what Ix, Iy, that is equal to VB minus Vc over R5 plus Ic, that is equal to VB minus VA over R4, and that sum must be equal to 0. Yes? are the yes, these are just, yes. I just label my equations. Okay. So now I see right away that I've written 2 of my 4 equations. I need one more equation for VC and another one for VD. And I ran out of space, so I'm not going to write those unless you feel that we should write another equation. Anybody feels we should write another one? Okay. Then we'll go on. So once we've done that, right, then we're going to have 4 equations, 4 unknowns, VA, VB, VC, VD, and consequently you can solve these equations. It's tedious, granted, but a computer could do that, yes.
And you source transformation to change I1 and R1 into a voltage?
You could. Unfortunately, it wouldn't help you a whole lot. Huh?
Well, actually, that particular source transform, I think it would.
Really?
Because we can convert the current source to a voltage source without generating another node to solve for.
Okay. We'll look at that. Maybe at some. Okay. So there are actually. I don't quite see it how we substantially would reduce that. Yes, we would have another voltage source. We would have no additional node, but.
We'd make one of our nodes known voltage. We'd make
Not really. If you think about it. So we're getting into details here. So I guess the question is. We're talking about these 2 or about these?
Those 2, yes.
Those here. Oh, yeah, you're right. Huh? Here, I guess it's 2. Here, if we would source, that's right, we could get rid of one equation. You're absolutely right. Yeah. Okay, I haven't seen that, but.
The other 2 wouldn't have the same.
Exactly, because there we would have a floating voltage source. Okay, so see, if you really have good insight, then you actually can simplify such a circuit very often a little bit beforehand, and then you end up with fewer equations. Okay, but anyways, no matter how you do it, you end up with a set of equations. You solve them for the node voltages. Afterwards, VA, VB, VC, VD, they're known quantities. And if you, for example, wanted to know what is the current IX, how would you go about that? Well, IX there, it's simply VB minus 0 divided by R3, right? That's it. So using this technique, we can find out the node voltage, and then usually finding the currents isn't that hard. Yes?
Is I1 VC minus VB or VB minus VC?
Is
IY.
IY is VB minus VC over R5.
Okay.
Right? Yeah. So.
Okay.
So notice also there I have IB and IZ. They're the same currents, but I put the arrows in opposite direction. It really doesn't matter at all, because all that happens in the equation is that these 2 terms, they would flip their orientation, right? So that's what I really meant with when you mark up your diagram. You know, you remember in the first or second week of class we had all these questions. But how do you know in which direction to draw the arrows? Well, I don't. I just draw them in any way, right? It really doesn't matter. Okay? Afterwards, the equation simply assigning the equation flips. All right. So I guess we're done with this one. We can solve this, and you're done. So now here is a special case. Sometimes, and again, the book explains this in more detail. Sometimes there are floating voltage sources, and then we need to apply a little bit more thinking. So the procedure is the same. If we want to solve, obviously here we could use probably some other technique like source transform, and we could solve this problem very simply, right? We don't want to do this here because I want to show you how to apply node voltage analysis to even this case, because I could have again made a monster example where you couldn't simply use source transform as in this simple one. So we proceed exactly the same way as otherwise. Why doesn't this? Okay, so we introduce a common node And then we figure out which node voltages are unknown. Well, I labeled those already. Those are Vy and Vx. Now, Vy and Vx are a little bit special here. First of all, they are related very closely. How they are related? What's the difference between these voltages? It's just V2. Vy minus Vx would be V2, right? And then there is one other thing that is special about the voltage source, and that's a little bit more subtle. Can anybody see that? Suppose that we wanted to write a node equation for Vx. Then we would simply add up all the currents, right, and set that sum to 0. That's Kirchhoff's current law. But what's the current through V2? It's unknown, right? We could introduce it as an unknown, and if we were a computer, then a computer would do that. Now, I'll show you a technique that is also in the book, which says, because node voltages Vx and Vy are related anyways, Vy is simply Vx plus V2, then we can treat this entire configuration here as one node. And the book actually calls this then a supernode. Okay? So now we actually have to write only one node equation, but it's a little bit special. So for that node equation, we are going to add up all the currents that are leaving that node. Okay? So we start with IA. So it's again IA plus IB plus IC equal to 0, right? Okay, so now we start with with IA, so that would be equal to Vy minus V1 divided by R1 plus I1, right, that's simply current IB now, plus IC, that would be Vx over R3 equals to 0, okay? Now, of course, in this equation, we have two unknowns, and we have only one equation. Therefore, we need one more equation. That equation is simply Vy minus Vx is equal to V2. And we can, of course, use this equation immediately to substitute in the equation above, and then we again have just one equation. Okay? So if we do that, then not only do we deal with the floating voltage source simply means a voltage source where neither of the two terminals, neither Vx nor Vy is connected to the common node. That means that it's floating. So then, whenever we have a floating voltage source, we get just one equation. It's the one here, and an additional one that we can substitute to eliminate one of the two voltages. Okay? You look puzzled. Are you, or can you formulate a question? Okay, so try to catch up, and in case come and ask us during office hours. Okay, thank you. Yes?
So the current through V2, which is VIB plus IC,
the current through V2, well, in this case, the current through V2 is equal to IA. Right? And so we can find out from that, we can find out easily what the current through V2 is. IA is equal to Vy divided, Vy minus V1 divided by R1, okay, which of course we know once we've solved these equations. More generally, of course, we could have a situation where both Vx and both nodes Vx and Vy, they have many components attached to them, and so then we would have to evaluate the currents in all of these individual ports and add them up. So then it's more work. There are other techniques where we actually would introduce a variable for the current through V2, and then we would have to have one more equation and solve for that one also. Yes?
Can you go to a last slide? I didn't get why we don't have three equations.
Here?
Yeah.
Why we don't have four equations?
Three equations.
Well, so I wrote only two, right? There are two more that I simply didn't write. There should be also an equation for VC and an equation for VD. Right? I simply didn't write them. Yes?
Coming back to the other problem. What difference does it make if we put IA coming out, right at the end?
If we
didn't circle like V2, Vx, and Vy like the way we did, we just make IA coming out Vx like that.
So then we would have two nodes, Vx and Vy, right? And we wouldn't know the current, so that would be one more equation, but we couldn't write Kirchhoff's law because we wouldn't know the current through V2.
But you just said the current through V2 is just V1 minus V1 divided by R1. Just said that.
Yeah, so that's what we essentially did, right? By making the circle around the entire node, where we just said, well, we don't really need to know what is the current through V2 because we make a larger shape and then we write it.
Why do we make Vy over here? If we just get IA coming off Vx, then IA just Vx.
That's absolutely fine too. Yes, you can do that.
All right.
Yeah.
I was just asking a similar question, Mike. So it's completely fine. Then you say the current through V2 is not known, but then if you draw like a Kirchhoff little circle around V2, then IA is going out on that side. So that means IA has to be coming in. So we do know the current into V2.
That's right. That's right. Yes. Yes. Sort of obviously we can find out what the current through V2 is, right? By applying enough KCL and Ohm's laws and so on, we can determine what that current is. But if we simply wanted to write an odd equation for Vx, and we didn't go and look through V2 what's hanging on the other side, then we wouldn't know what to write for that current. We could, and computer programs that simulate such circuits, they simply introduce an additional variable for the current through V2, and then they have one more equation, they solve for that also. That's fine too. And now you probably know enough about Kirchhoff's laws and so on that you can, by inspection, devise all sorts of rules on how to deal with such problems. In fact, I do not remember this stuff. I think about KCL and then make it up on the go. Okay? And so you may do that. And then you come up with different techniques. In fact, just when I looked at my slides this morning before coming to class, I was debating with myself, should I present you this form or another technique on how to solve this? But then I figured that I wrote already a comment that would be confusing otherwise. Yes, I guess you first.
So can we instead of doing supernet, can we just write Vy equals Vx plus V2 and V2 minus?
Yes, we can do that, and then we could, of course, we of course could immediately here, instead of even writing Vy, we could have said, well, this is Vx plus V2, and we could have put Vx plus V2 here, and then we never would have had to write this equation. I think the book actually does that. I thought I write it separately, this equation, to make it a little bit clearer. Substituting this here obviously is trivial, and so if you can do it in one single step, hey, by all means, do that. Yes?
So the fact that V2 is not connected to our node, that makes V2 a floating.
Exactly, yes. Good point, yes.
I have a question about the previous problem. Was
Sorry, I know, I read it once, and I have absolutely no clue anymore. What's the essential node? Anybody else knows? Yes.
it's connected to your branches.
3 or more branches?
But VC, V8.
Well, then VD would be an essential node because it's connected to branch I1, R1, and R6. That's 3. One of these days when I have the time, I'll write my own book because I don't know why we need to know about essential nodes. I knew about them, and it's never. But sorry about that. We have to put up with that book. So So if it's a problem, then I'll be happy to go and read the chapter about essential nodes, and then we can discuss that in more detail. But the way we solve, the way I explain it to you, you really don't know about essential nodes. You need to figure out which nodes are the unknown node voltages. Where do you not know the node voltage? Well, here you don't know it, here you don't know it, and there are two other ones, right? Done. That's it. Okay? And whether they are essential or non-essential, I mean, every node is essential, otherwise you wouldn't draw it in the circuit diagram, right? Kind of bizarre. So that's the thing, right? You don't get to pick your perfect book unless you write it yourself. Yes?
So anyway, you got to solve the system of equations. You got to solve the system of equations, right?
Yes. Yes.
Are there other ways to avoid that?
To simply avoid, if you have a way to solve complicated design problems without solving any equations,
What if the circuit has more nodes than branches to it?
If a circuit has more nodes than what?
And branches, so there will be more equations to solve.
Yeah, exactly. Yes. I mean, there were. You imagine we talked about microprocessors. They have 1.2 billion components, transistors. They have 3 terminals each. Imagine how many nodes these circuits have. It's just, it's billions of nodes. Okay, or at least hundreds of millions, I guess. Some of them are joined together. Yes. So what you do in that case is that you will simplify and we will talk about, hopefully still later this week or beginning next week, we'll talk about techniques that you do not always need to consider an entire circuit all at once, right? For example, if you were to design a laptop, the laptop needs to have a power supply, but it also needs to have a computer inside, right? Well, if you do it right, you design the power supply, and you design it well, so the power supply afterwards behaves just like an ideal voltage source, possibly with an output resistance or 2, but then you have that complicated thing that may contain a few hundred components and a microprocessor and God knows what all by itself. You're sort of done with that one. You wrapped it up into just 1 or 2 simple symbols, and then you go and focus your attention on the computer part. And of course, that one you dissect further. But yes, hey, at some point, you will have to deal with sets of equations. Now, that said, in the exams and even in the assignments, I try to not make this into a math class. Okay? So, especially in the exams, I try very hard not to end up with more than 2 equations, but occasionally there are 3. Okay? So be ready that in the exam, it might be that 3 equations, simultaneous equations, come your way. That's not the first time that you've seen that, right? But most of the time it will be only 2. Actually, that said, can we go on to the next example? So now, that said, let's look at this example here. Let's try to solve this blindly. So again, we assign a common node here. And then we figure out what the unknown nodes are. I just label them with color. So there's 3 unknown nodes. Oh, there is one more here. 4 unknown nodes. Oh, exactly. So now we have 1, 2, 3, 4, 5 unknown node voltages. How many equations does this? We get 5 equations, right? And so if we blindly apply our schema, then we end up with 5 equations. They'll be perfectly fine. If we know how to deal with 5 equations, we're going to get the right answer. But it's a chore, right? Okay, so now I guess some of you already caught, yes?
We really need to know between R6 and R8. I mean, we can just say plus in the denominator, right?
Exactly. So now we can make all sorts of simplification, obviously, first. So you just mentioned this one here. Well, we simply replace this by R6 plus R8. And then afterwards, if we wanted to know the voltage in between, what would you do? Well, basically it's a voltage divider, right? And we have many ways on how to solve for the voltage in the middle of a voltage divider, right? So, so what about, what are there other opportunities, other things we can simplify? Yeah.
That is then in parallel with R5.
Okay, fine. You see that? So then we have this in parallel with R5. What about R7? Yeah, I mean, certainly R7, does it dissipate power? Yes. Right, so if we wanted to know how much it power dissipates, then we cannot just ignore it, right? But if we just want to figure out the node voltage at this point, we really don't need R7. That node voltage is set by V1. Remember, V1 says the voltage there is V1, and I don't care how much current I need to deliver. I just deliver enough of it so that the voltage is V1. Any other elements that can be eliminated? Which one? R4, yes. Very good. Why? Yeah, exactly. The current through this entire branch is I1. And of course, there is going to be a voltage drop across R4. But it does not change the voltage at this and this node. Okay? Okay? So, actually then, at this point, I probably would redraw the circuit, right? Let me see if I can do that. R2, I1, R3, that would be this R6, 8, 5. That's this one, okay? And then we have a voltage source here. That would be V1, okay? R1. Okay, and now we find out what are our unknowns. Well, this, right? Those are the two unknown node voltages. Now we can figure out what those are. We can then say, well, that's really this node and this node. And once we have those, we can figure out in the real original circuit what all the other unknown node voltages are. But we only needed two equations to solve this one. And of course, now at this point, yeah, probably you could, maybe you could do this even some other way. Yeah.
I'm sorry, but why can you get rid of R7?
R7. Okay. When we are applying node voltage analysis, the one thing that we are going to find out is the node voltages. Okay. Now, anything that does not change the node voltages is, and now I copied the book maybe in a slightly different sense, is unessential. Right? So if what's the node voltage here? Zero, right? What's the node voltage here? V1. It doesn't matter what R7 is. Of course, you could say, well, I make R7 0, but that's not a realistic case. Like, it couldn't be practice. Yeah? Okay? Yes?
If you had, like, instead of that high current source, if you had a voltage source, like, how would you apply the floating voltage?
Okay, we can do that. We can say... Yeah, so we can change this, that this is a voltage source here, plus, minus. So then we simply would apply, we would again make this well, actually, if this was a voltage source, then let's first of all get rid of R3, right? Okay, and then afterwards we again would so this guy is now gone, and then we have this current, this current, this current. We would add all of those up, get one nodal equation for that, and then we know the difference between the two voltages. Okay. Yes.
If it's a voltage source, can you still get rid of R4?
No, then we could not have gotten rid of R4, yes. so when I simply made that into a voltage source, I sort of jumped a little bit. We divorced ourselves from the original circuit. So be careful when you now go and download this from the web. This conversion to the voltage source wasn't really right. It simply was an example, but a different one, yes.
The second blue line circuit you just draw is if you flip the independent source I and R3, like flip their position, it will be an equivalent circuit.
If I, oh yeah, sure, I can do that anytime, and I can source transform them, whatever I like. Yeah. So the topology, right, where exactly I put my elements is totally irrelevant. Just avoid really ugly schematics. And so here, this is also something that I recommend, right? And it really puzzles me when I see midterms and people have made mistakes in midterms. Right? You mark up something like I just did this diagram above, and it gets a big mess. I mean, agreed, it gets a big mess. And you know, you really have the time, redraw it, because more than 50% of you are like me. Out of a mess, you get a mess, and the mess is not the correct answer, right? So just redraw it. Doesn't cost you much. It costs you a minute, but you save 10 minutes trying to find a mistake and possibly not finding it. Yes? The resistor R4. Okay, so the thing is, when I want to write a KCL equation here, what is the current flowing in this branch here that includes the resistor R4? It's I1, right? It really doesn't matter whether there is a resistor R4 and what its value is. Could be anything, right? Likewise, if I'm at this node here, the current that's flowing in this direction is I1, totally regardless of what the resistor R4 is. So I really can save myself an equation, not bothering to include the node in the middle. Afterwards, if I wanted to know what the voltage is here, well, I would use the voltage here, and then I know the voltage drop because R4, well, that is equal to I1 times R4, so it would be, let's call this the voltage VC. And then this voltage would simply be equal to VC plus I4 times R4. Right? I1 times R4. I1. Okay? So, did I have to do this? Well, no, but we could have started solving this thing and we would have ended up with 5 equations. If we solve them correctly, we get all the right answers. By applying this trick of saying, hey, you know, I really know the current flowing through R4, and therefore I don't need to write an equation for the node between I1 and R4. We saved ourselves one equation, and then we had a few other places where we saved ourselves an equation here and there, and in the end, we end up with a circuit that has just 2 equations. Now, I totally admit that this is a little bit a contrived example, right? I really loaded it up with all sorts of crazy, stupid things that probably wouldn't happen in a real circuit in all this combination, but we'll get those. And, you know, I may put something like this on the exam. Why? Well, because if you can deal with this, then either you're a math ass, but most of us are not, right? But more likely, you actually really understood how the circuits work, right? So be careful in the exam. There may be a problem like this one. Maybe I even recycled this from an earlier exam. There may be a problem like this one, and if you blindly apply node voltage analysis, you will end up with 5 equations, and after the exam you will say, this was the stupidest exam in the world, this was just math. Well, that's one way to look at it. Another way is here, you transform it a little bit, you get two equations, sometimes just one, and it's trivial to solve. Okay? And so there we'll get sort of, hopefully, 90% of the class goes this right and 10% complains. I would like that 100%. Because that's solve it. Okay? Any more questions? All right. So here I write the procedure that we use like a recipe, like something that could be programmed. You pick a common node unless there is already one. Enable all node voltages. Simplify the circuit to minimize the number of unknowns. That's what we just did, right? Really do that. Otherwise, chances are you end up with more unknowns than necessary, and then it's a mass headache. Write KCL for each unknown. Only the unknown voltages, of course. You need to write an equation for. Solve for the node voltages. And then if you want to know branch currents, well, you need to use the element equations for that, like Ohm's law. Okay? God knows why this moves around like this, but we just have 10 minutes to look at one more thing. The systems that we are dealing with so far have been linear systems, right? The relationships of, well, we just basically had resistors, they are all on straight lines, okay? So for linear systems, what happens, and that's true in general, and we have heard about that also in EE20 or in any other class, there's a bunch of inputs, it has, in this case, just one output. Well, the output is really a linear superposition of all the inputs, okay? It's surprised, yes?
Why can't you assume a circuit is linear?
Well, you can't assume it. All the elements that you use in that circuit have to be linear, but because we only have resistors, then the circuit is actually linear. You got to be a little bit careful. If you put one voltage source into the circuit, it's no longer linear. Because now, of course, if one of these terms is constant, well, it's no longer proportional to an input, right? But doesn't need to bother us, right? If a resistive circuit is linear, okay? Now, very simple concept, right? So I repeat it. In a linear circuit, really the output is the sum of the first input times some coefficient, plus the second input times some coefficient, and so on. Now, why is this interesting? Well, it's interesting because, for example, we could let's suppose that our circuit had only just two inputs. We could figure out what the total output is by first setting SI1, the second input, to 0, figure out what the output is, then we essentially would calculate K1. Then afterwards we set this guy to 0, we figure out what the output is, then we get this term, then we add them together, and we're done. Okay? Now this may sound more puzzling than it is, so let's look at an example. Okay? So here again, this is, if you're a computer, or if you think like a computer, or maybe a mathematician, then you may like this, right? And otherwise, just come along for the ride of the example. So what we want to do is we have this circuit here above. It's a very simple circuit, so the point of this is not to show you something great new, but to explain an idea. Okay? So it has two sources, V1 and I1. We want to figure out what is the current IX. Okay? So the way we are going to do this now is by using this idea of superposition. Right? So what does it mean that we use the idea of superposition? Well, we are going to figure out what is the contribution to IX from the voltage source, V1, and then we are going to separately find out what is the contribution to IX from the current source, I2. Once we have both of these contributions, so that be this term and this term, we'll add them together and we get the total correct result for IX. Okay? I write these strange S's there because, hey, it's totally general. It doesn't matter whether it's a voltage or a current, or it could be anything else as long as we have a linear system. Okay? Of course, in EE40, it's going to be either voltage or current. All right, so the step one, we now have this circuit here. In the step one, we make the current I1 equal to 0. Basically, what we make is that this term here is 0, and then we get only this term, right? Okay. And well, what's a current source that has a current 0? Well, it's like there was nothing there. So I just removed it from the diagram. Then we figure out what is this current I1. And well, I'll let you figure that out. We could, I guess, figure out what this voltage is. So that would be V1 times R3 in parallel is R2 plus R4, okay, divided by R1 plus R3 in parallel with R2 plus R4. So that's the voltage Vx that we have now. And now we have to divide that by the resistance through which that current is flowing, so divided by R2 plus R4. Okay? So one way to solve it. I hope I did it right. Yes?
It's like, if you sort of transform V1 and R1 to I, like current source, then wouldn't it be like R1, R3 will be like parallel?
Yes.
So should we just, because we said R1 plus R3, should we just like find out if one's parallel?
Okay, so what I did is I used voltage divider. So, but you're absolutely right. You can do this source transform. You can source transform this into a current source, and then you actually could use the current divider. Yeah? Either work fine. Actually, your technique is perhaps a little bit preferable, would end up with a slightly simpler equation to simplify what. Again, there are lots of ways now. Now you have lots of techniques on how to solve these circuits. Okay? Any more questions about that? So again, hey, if this was a little bit quick writing this equation, you're not limited to solving the circuit this way. Okay? So likewise, now in step 2, we make the voltage source V1 equal to 0. So we have, again, this was the original circuit. Now we make the voltage source 0. We don't make the current source equal to 0. So that's here. So the voltage source 0, well, that I replaced it with a short circuit. And I figure out again, and I'm not going to write it, the equation, right? You can figure out now what Ix would be. And the point, of course, is because now the circuit is simple, it has only one source anymore, it's easier to solve, right? For example, I could not have written an equation for Ix as I did here, for this circuit here right away, but for the circuit here, where there wasn't a current source, I could do it right away by inspection. Okay. Likewise, we get a current here. I assume that you do this correctly, and then we have Ix is equal to this Ix1, the contribution due to the current source, plus Ix2, the contribution due to the voltage source. And that's the correct Ix, even though we analyze two different circuits, yes. No. Okay? I thought you had a question. All right, so again, hey, you know, it's actually something very, very simple, applies to all linear circuits, and it's very convenient. Sometimes it really makes a big difference. We can solve a circuit more quickly by knowing about this. Let me just use 1 minute to summarize what we know now. So first of all, we know all sorts of special tricks about how to deal with circuits. Series, parallel, dividers, source transforms, and so on. Don't forget that, right? Then we know the node voltage analysis technique that allows us to deal with anything that doesn't fit into the first category. First category, usually simpler because we don't end up with a very large number of equations. But the second category is general, okay? And then superposition, that's just what we learned about in the last last 5 minutes or so, that sometimes also helps to simplify a circuit. And we'll find other tricks as we go. Okay? So I told you already in exams, that's for the lawyers. I make sure that I'm covered. Usually this number will be 2, but you know, if it's 3, then I'm legally protected. Okay? See you Wednesday, yes.